Is a extensive deep dive on neural networks. So we'll be learning about neural networks in the first 2 sessions, and then Ashish is going to come talk to us at the end of the day about what's the latest and greatest things that are happening with deep learning, which we've heard sprinkled throughout the week, but today I think we're going to start to really develop some intuition for what's going on there. Brett is going to be leading most of the introduction. He's taking on the Herculean task of dealing with you till about 4:30. I'll be walking around as well, but without further ado, let's get into our introduction to neural networks from Brett.
I'm Brett. I'm going to be talking about neural networks. Just a little bit about me. I'm a postdoc at UC Berkeley. One of the projects I work on is this Python library and web package called Cesium for doing machine learning with time series data. If you have interesting time series data you want to do machine learning with, you should definitely come talk to me. I would love to hear all about it. You can also check out our website, cesium.ml. I'm also going to be working on the new Marshall for ZTF. So if you do anything with PTF, I don't really know that much about the project yet. I'm sort of just getting started. So if you have requests for how you would like to interact with your ZTF data, you should also come talk to me. And then, excuse me, the last thing that I work on is I do some deep learning neural network stuff with time series data. But today I'm just going to be talking about, very general, super basics. Adam called it a deep dive. I would call it more like barely scratching the surface. It's a very, very big field, but very exciting. I think we've already heard probably 6 people talk about it in their lectures. So, okay. So why are we interested in neural networks? At the most basic level, they're just a very general class of statistical model. So you have some data, and you maybe don't know exactly what functional form, what probability of distribution your data comes from. So neural networks are just a way of encoding a very wide variety of models and kind of learning interesting statistical patterns in your data. It's a very superficial explanation. The reason that we're interested in neural networks right now is because at the moment they're giving the state-of-the-art performance in just about every prediction task in machine learning right now. So computer vision is a big one, we've already heard about that. But also everything from speech recognition to natural language processing, probably something else since I started talking. It's really like a new neural network application every day comes out and crushes whatever the state of the art was in that field. It's quite crazy the pace at which these things are taking over. So there's a whole lot of hype. Depending on who you ask, maybe not all of it's justified, but I think there's really no question that for a huge variety of tasks, by far the best way of solving it at this point in time is to use some kind of neural network. Maybe that you yourself didn't train, but maybe to use someone else's neural network solution. Okay, so I'm not going to really go that much into the history of neural networks, but just an extremely brief breakdown. The reason that these things are called neural networks is because they have sort of a biological inspiration. So the idea being that your brain is made up of all these neurons, and each one individually is extremely simple. All it really does is take some sort of input current and output some sort of other output current. But in combination, if you have billions and billions of these units, they can learn to represent and interpret really complicated patterns. So that's basically the intuition behind why this thing is called a neural network. We're going to have a sort of graph structure like this, where inputs feed into intermediate cells, and those feed into other cells, and basically we have these activation levels firing between different parts of our network. And at the end, we hope that we get out some sort of complicated, interesting function of our input that we can use to do classification or prediction, inference, etc. So they've actually been around for an extremely long time. Nothing about what I'm going to talk about in this session is at all new. In particular, they've been used since the 80s and 90s, I think, to do handwritten digit recognition. But a lot of people back then thought that they were really a narrow class of model. There was sort of a lot of hype in like the 40s and 50s when they first came out. People thought that we would be able to simulate human brains by like 19 1958 or something. And that turned out not to be true at all. So they sort of fell into disregard for a while. This network down here is one that was popular in the 90s for doing digit recognition. It's called LENet. Jan LeCun at NYU is one of the sort of foundational people in this field. And it actually looks a whole lot like the networks that we're going to see later. And this came out in the 90s. Basically, this is the same architecture that Ashish is going to be talking about later, maybe a few different bells and whistles. But the theory of this really hasn't changed very much since the 80s or 90s, at least at the level that we're going to be interested in. So what happened in the last, I would say, 7 years, maybe other people would disagree, is that people sort of started looking at these algorithms again, and this time there were a few other things going in their favor. One is just that because of the internet, the amount of data that people could get to feed to these algorithms is many, many orders of magnitude bigger. And it turns out that the volume of data you have makes a huge difference for training these algorithms. Another thing is just that computers are much more powerful today, and it turned out that the amount of computing that you need to do to get an effective neural network model like this is quite large, and they just didn't have the resources back then. So also the advances in GPU computing, people figured out ways to run these algorithms on GPUs, and it sped things up by, I don't know, let's say 1 to 1.5 orders of magnitude. And that was another big sort of advance, maybe not as big as the amount of data increase, but still enough to really like turn these things from sort of novel and interesting to like crushing every single problem they come into contact with. And then another thing is actually just that people sort of, once it became clear that these algorithms did have something more to them than people realized, people started experimenting more with different optimization techniques. So different mathematical algorithms for training the networks. And it turns out that, we'll talk about this more later, because of the sort of complicated structure of these networks, training the algorithm and finding a good set of parameters is quite difficult. It's much more difficult than with all of the other statistical and machine learning algorithms that we've talked about. So the way you initialize your parameters, the way you search for improvements in your weights actually makes a huge difference in whether you ever get to a good solution or not. So you'll see this in your exercises too. If you sort of mess with your parameters, you can easily run the same algorithm and just have it converge to a garbage answer that gives you completely noise classifications. So people have just become a lot better at kind of identifying best practices for training these things, and that's made a huge difference as well. So just a little diagram here to show you what I'm talking about. There's this very important data set called ImageNet that consists of millions of images from many, many, many classes, and it's a very hard classification problem. So this here is an image classification competition that's held annually. This is the top 5 error, which means was the true class in the top 5 classes that you predicted. And so you can see just in 2010, which at least for me that wasn't very long ago, maybe to you okay. The error was almost at 30%. And then every year it just started moving down. I forget why this is purple from the context, but I think this was some different algorithm they used. But you can see here, human level accuracy is about a 3.5% error rate. Like I said, it's a pretty hard classification task. It's like distinguishing between spaniels and beagles and stuff like that. It's not like dog or boat. So at this point, we're basically at human level accuracy for this specific task. I would not claim that we're at human level accuracy for every computer vision task. But we're sort of moving in that direction in a surprising number of fields. And that was only 2015, so 2016.
So 2016 we exceeded that.
2016 we've exceeded human level accuracy, so we're now all irrelevant. Okay, so moving back from the big crazy convolutional network stuff, I'm going to go over just the very simplest kind of network. It's called a Perceptron Network. This is sort of the thing that I mentioned that back in the 50s people thought was going to take over the world and lead to immediate human level intelligence. Didn't work out that way, but it's still an important kind of building block to understand. So basically the way that this works is we have a kind of graph structure. We have nodes that represent either input values, output values, or some sort of intermediate computed values. And then we have edges that represent, for now I'll just say, some kind of functions. So you might think of this, and we'll see some examples of more specifics, but multiplying this by some value and multiplying this by some value and adding them together. That could be one example of a layer in this perceptron. So it's really just a certain kind of structure for defining a function f that takes our inputs and goes to some outputs. But we have these sort of intermediate layers that are going to serve the same role as neurons in the human brain, maybe, if we play our cards right. Okay, so stepping back even more, this is literally, I think, the simplest possible neural network. So we have an input, we have some sort of weight that we're going to multiply by, basically just like in this setting here where I have this edge, and I said that maybe you could consider that multiplication. That's what we're going to do here. We just have a single scalar input. We're going to multiply by some weight. We're also going to add a bias term. A lot of the time, people will just sort of leave out the biases in these. But just like linear regression, you just sort of add it in at the end. It's not really, doesn't really change any of the mathematics. So we just have these simple operations, and we go from an input to an output. And hopefully people can tell that this is just another way of representing a linear regression model. So the linear regression problem would be to take a whole bunch of inputs and outputs and find the optimal slope and intercept to sort of fit a line to that data. And that's exactly the model that we've represented here in this sort of graphical perceptron form. Does that make sense to everybody? Okay, great. Okay, the second simplest neural network that I can think of is basically just multivariate linear regression. So in this case, we have two inputs. We still only have a single scalar output. For each input, we have a coefficient, a regression coefficient, or a weight, we're going to be calling them in this context. And then we also are going to add some bias term. So this is just a two-dimensional linear regression model. Hopefully that is also pretty clear to people. Okay, so one more sort of wrinkle we can throw into this is if we take our simple linear regression model that we saw here, and we apply this sigmoid function to the output. I forget if people said that they were familiar with logistic regression, but that's exactly what we're doing here, is we're taking some sort of linear output y, and we're squashing it with this activation function to lie between 0 and 1. So basically, we're just turning a value into a probability. So if our estimated value is 0, we're going to say we're sort of neutral on the prediction, and we say probability 0.5. If our estimated value is very high, then we're predicting high probability of true or of whatever class we're interested in. And if it's very negative, then we're going to have a probability getting close to 0. Does that make sense to everybody? Great, okay. So these are all very, very, very simple examples of neural networks, but I think that it's important to understand kind of the building blocks before we move on to the more complicated stuff. Okay, so this looks more complicated. It really isn't, though. This is basically just the natural next step when we move from multiple inputs and a single class that we're trying to predict. Now we're going to have multiple classes that we're trying to distinguish between. So have people heard of the softmax function? Is that something that people are familiar with? Getting mostly no's. Okay, so basically all that this means is, like before, we take our inputs, we multiply by our regression coefficients, we add our different bias terms, and now, like before, we're going to have several different values y like this. We're going to pass each one to a sigmoid function, so each one gets squashed into a 0 to 1 range. But we want the values to add up to 1, so then we just divide by the sum. That's basically how you can think of the softmax function, is it's just turning the individual sort of probability scores into an actual proper probability vector. So the things that are going to come out of this classification are our estimated probabilities for each class. Did we do a logistic regression example ever, or anything like that? We did something with random forests, maybe? Yeah. So when you do predict probability with random forests, what you get out is an estimated probability for each class, right? Yeah, it's true. This is basically just going to be exactly the same thing. We just have this different kind of networky structure for doing it. But this is still just a multi-class linear classification. The scores for each class, sort of the thing before the softmax, are a linear function of the inputs, and then we convert them into probabilities with this softmax function. So this is still, although the graph is a little bit messy, this is still a very, very simple classifier. This doesn't have any sort of, I guess it has some interesting properties, but it doesn't have any like cool neural networky specific properties. Okay, I'm gonna do, has anyone happened to check if we have Wi-Fi yet? I was gonna have.
Yeah, it's back.
Oh, okay, great. Okay, so I liked this little thing just to play around with a bit. Let me go back to the slide. I meant to make like a short link version of this, but if people just want to copy this link down, you're all fast typists, I assume. So we're just going to do a little like playing around with these sort of weights and sort of get some intuition of how the networks change. And I'll be doing it too, but it's just more fun if you get to play along. Okay, so I'm going to click on the link. You can still copy it from my browser if you probably. You can read that. Visual interactive guide, basics neural networks.
I also would guess if you Googled Jalamar train your dragon, it will be the first hit you get.
It's probably a more efficient way. So I'm going to scroll back up and go through a little bit more of this. So this is where I got some of these visualizations from. It's a pretty cool. This is very, very basic. So I didn't want to go through this whole thing. But this is really just sort of giving you some intuition for how we play around with these weights and biases. And our goal, when we get to the training neural networks bit in just a few minutes, is going to be to come up with some automated way to find weights that match our dragon. I don't know why it's called that. Oh, there's like a movie or something about training dragons. You guys probably know. So I'm apparently doing well according to the little thing. Yeah, so maybe just I don't know, take a few minutes and kind of play around with these weights. There's a couple of different little widgets here. So there's a multi-dimensional one down here. In that case, you can't actually see the data that you're fitting anymore, unless I guess they could have done some crazy 3D visualization. So you just, in that case, all you have available is this loss function, and so it sort of becomes like a, guess and correct exercise. I don't know, maybe take 2 minutes and play around with this stuff. I don't want to get too carried away. Did we get an error lower than 565 on this one? If so, you have to come teach the rest of it.
What did you say, 565?
Yeah.
They got 530.
Whoa.
Up at 497.
Wow. You guys are too good.
You got one better, was calling you an overlord.
Oh yeah?
Yeah.
My mouse speed is very, very fast, so it's hard for me to fine tune. My learning rate is too high. We'll get that joke later, it'll be hilarious.
You should be able to type things in there, right? Rather than having to slide things.
I guess you could probably open the JavaScript.
550.
So
515.
okay, so people.
Oh,
What's that?
doesn't matter. You're in error.
Okay, so people probably understand now kind of what's going on when you change these weights around. The only other thing that I'll just mention briefly, and I'm going to get back to this, but just since it's here and maybe people are wondering, these buttons that say GD step. So we're going to talk about this in a lot of detail. This means that it's going to take a gradient descent step. Just for my future reference later, how many people know what gradient descent is? Okay, cool. We're going to talk about it, so not a big deal. But for now, I'll just say that what this means is they're using calculus to figure out a good choice of update for these weights. So it's automatically changing the weights in a way that decreases the error by a little bit. And if you do it a whole bunch of times, then your error is going to start decreasing to something smaller. And that's basically the gist of how you optimize your neural network, but it's a much more complicated version of that. The only other thing I'll show from from this little demo is this bit here is kind of fun to play around with down in the classification section. All we're doing here is we're looking at how the network architecture changes as a function of the number of inputs and classes. So it really quickly becomes impractical to visualize a network in this way with all of the weights and all of the biases, all of the inputs and outputs. If you think about it, the number of weights that we're going to have here is, go back to a smaller number just to make it a bit easier. So we want to get, we have 2 numbers going in, we have 3 numbers going out. So basically what we're doing in multivariate regression terms is we're coming up with a 2x3 coefficient matrix that we're going to multiply the input by. And we're adding a 3-dimensional vector of intercepts. And then we also have this softmax step. But like we said, that's just rescaling effectively. So I guess the main intuition to take away here is that the more classes you have and the more features you have, the more complicated a network you need to represent all of these connections. Later on, we're going to have networks with more than one layer. So right now, this is really just a single function that goes from input to output. But as we sort of stack these things together, you really have to be careful with the sizes of your layers. And you have to sort of be able to reason, maybe not do the exact calculation, but reason in rough back of the envelope terms about how many parameters you're adding to your model as you increase the number of features or classes or the size of these intermediate layers. So that's the only sort of takeaway from this that I think is important. Okay, so back to my slides. Okay, so I'm gonna digress a little bit. Actually, let me go back to my little neuron here. So in this neuron example, the neurons here don't simply take a combination of inputs and forward the full amount of the input that they receive. What they do in practice, if I'm offending anyone who actually knows about biology, I apologize. But basically what they do is they accumulate the different input signals and they pass them through some kind of activation function. I think it looks sort of roughly like the sigmoid function in practice, but basically if you have a very small input, you're going to get a very small output. But if you have an enormous input, there's some sort of cap on the output that you can get. That's one way to think of what the sigmoid function is doing. The only important thing for us is this is some non-linear function that's combining all of the inputs and turning it into an output signal. So it's called an activation function because of the biological sort of neuron connection. But in our case, we're just going to call, we're going to use the term activation function to refer to some function that we apply to an output here before we send it on to the next level. Does that make sense? Was that too like convoluted? For now, you just sort of have to take my word for it that this is a good idea. I'll get into why we want to do that in just a second. But the biological connection is pretty straightforward. This is just how neurons work. There's some sort of non-linear function of the input that gets passed on to the next neuron. And it turns out that by doing that, we can sort of construct very complicated non-linear functions. Before, we were only looking at linear functions of the input, but obviously the relationship between our predictions and our data doesn't always have to be linear. So now we're going to talk about how to introduce non-linearities. I guess, most convincing reason for me why these activation functions are a good idea is there's this thing called the universal representation theorem, which says that if you have a single layer network like this one, and you, instead of just passing these values on to here, if you apply some nonlinear function to each one and then recombine them, you can actually train a network that looks just like this, no more complicated than that, to represent any function to arbitrary precision. And that's a pretty crazy, like, surprising result, at least to me. But it doesn't make any claim about the size of the hidden layer that you have to have here. So basically all that it's saying is that by combining a crazy huge number of simple nonlinear features in some sort of network structure like this, we can represent any arbitrary nonlinear function. So I don't know what the proof of that looks like. I think it's somewhat complicated. But basically you just need to know that that is a thing that is true, and that's sort of the overall motivation for why we want to use these nonlinearities in our network, is because we want to be able to produce a nonlinear function as output. So the most common activation functions that people use are these three here, Sigmoid, tanh, and relu. They all sort of have a different structure. You should sort of familiarize yourself with what these different shapes look like, because they come up all the time and we're going to be using them a bit later on. Sigmoid we've already talked about. It sort of squashes something from the number line into a 0 to 1 probability scale. Tanh, instead of going from 0 to 1, goes from -1 to 1. I think tanh is quite a bit more popular than Sigmoid these days. The reasons for using different activation functions are very mysterious and magical. People just sort of try different stuff, and because they have some hunch that it might work, and then it does, and everyone starts using it. It's really not more rigorous than that, unfortunately. And then the last one is this relu function, that stands for rectified linear unit. And as you can see, it's basically just taking the identity function, y equals x, and it's clipping it at 0. So this is almost a linear function, but it's actually nonlinear. It's a piecewise linear thing. And it turns out that even with something as simple as relu activations, if we apply those in our simple little perceptron network, we can still represent an arbitrarily complicated function of our inputs. And these are quite easy to compute because it's just very, very, very simple. There's no floating point arithmetic going on. It's just you either take the value or you take 0. So do people sort of have some kind, are people vaguely convinced that these activation functions are a plausible thing that we might want to include in our network? That's really all that I expect at this point. Are you not convinced?
Well, how do you normalize the probability into tanh?
Oh yeah, sorry. That's a very good question. I think I probably misspoke a little bit. So the reason that we originally cared about the sigmoid function was because it sort of squashed something into the probability ring. But in terms of an activation function in general, we don't need that to be the case. So all these are doing are taking the input and passing it through some nonlinear function. Intuitively, it seems like these activation functions should be increasing. They should represent that the neuron, as it sees something that it sort of recognizes, input or outputs more and more signal to the next neuron down the line. Turns out that that's not even important. There are plenty of activation functions that aren't even increasing. Those are completely biologically implausible. These are all sort of vaguely the same shape, and I guess that's appealing. But like I said, people just at any nonlinear function you can try as an activation function if you want. These are all just sort of similar things that people have coalesced around as popular choices. Yeah.
So, for example, for the sigmoid, how do you define an effective, I guess, temperature for your x? Because you need to. It seems like if you have an x that goes from 100,000 to 1 million, that's going to give you a very different result for your sigmoid than you have an x that goes from 0 to 1.
Yeah, that's actually a really, really good question. That is a huge problem in neural networks. I have a slide about it coming up pretty soon, but there is a common problem where you're training your neural network and a neuron falls into a state where it's only outputting values in the tails over here. And that has big implications for training your network, because if you think about it, this function is flat here. The derivative is basically 0, and the derivative is basically 0. Here the derivative is exactly 0. What that means is, when we're trying to train our network, we look at the slopes of these functions and we try to sort of jitter them one way. We jitter the parameters one way or the other and see how it affects our loss function. Down here, there's no effect on the loss function. It doesn't matter which value you output if you're already down here. And so these neurons are effectively just dead. They no longer will get updated during the training process. So the way that you do that is, remember before when I said that people came up with very clever ways to initialize these things? You just don't let that happen. You are very careful to make sure that the values that get passed into this are kind of in the nice range. And if that doesn't happen, then big parts of your network will just sort of turn off. Yeah, it's very complicated, but yeah, that's a really good point. I think in some networks maybe they also have a tuning for like the slope here, but for the most part you just are careful with the scaling of your inputs, and you're careful to take little steps so that you don't end up shooting all the way down here. I know that's sort of a hand-wavy explanation, but it really is like a very fundamental problem of training these networks. Okay, so far we've only talked about the most boring single-layer network. This term deep learning refers to very deep networks. They don't look like this still, but obviously you know that we're going to want to stack multiple layers like this on top of each other. And so the idea is, just like before, we have some function of our input that we store in this hidden layer. We feed the values in the hidden layer through some activation function, and then those become the inputs to the next hidden layer. So we have some other function here. We have the new second hidden layer. We feed those through the activation function, go to the third, feed those through the activation function, and then those are our outputs. So in maybe one example, we could have like just a linear like multiplication here, and then feed these through the tanh function, multiplication, feed these through the tanh function, multiplication, and then we'll feed these through the softmax function, because at the end we want the things to be output as a probability vector. Does this make sense? People, okay, should be pretty straightforward. The basic idea is that if we have a lot of different connections between these different layers, then we're able to represent more complicated functions without growing our network to a super, super large number of parameters. it's sort of an open research question, I think, of why deeper networks tend to perform better than shallower networks. That's not even always true, but there's, for this same number of parameters, we have 15 different hidden units here. If we took those and stacked them all in the first unit, you might think that they would sort of represent the same complexity of functions, and it just turns out that's not true. By sort of like how the brain works, it turns out that having a bunch of connections in a row between these very simple units is just a better way to represent things. Maybe Ashish is
So
going to
there
have
is one
some.
biological connection here in our brain. How the neurons are connected to each other. Some neurons are very long, and so they come from another part of the brain, really. And those inputs, I'm not completely sure how that gets. I don't know whether we all are completely sure of how that gets connected, but it is found that when there are people who have dementia, it is those neurons that get affected first. So very likely it plays a high role in doing a high-level connectivity of different concepts. And something similar does happen in multi-layer neural networks. So people have been trying to program it that way. I don't know how far you can stretch the parallels, but that's one of the things that does happen with multiple layers.
Yeah, I think people sort of go back and forth on, or maybe it's a matter of personal opinion, on whether these like biological motivations are important. They're definitely important for the history, and they definitely have inspired a lot of good ideas. I think people now are starting to move more and more away from the sort of brain-focused way of developing network structures. But there are a lot of really interesting connections between how the two work. So basically, for now, just sort of take my word for it that if you have a deeper structure, a deeper network, you're able to represent more complicated, a wider variety of outputs than if you had a shallower structure with the same number of units. The problem that we're going to run into is that deeper networks are also harder to train for reasons like we just talked about. Each time you pass through an activation function, you're sort of running the risk of having weird stuff happen with your gradients, and in the end it can end up that your network doesn't train well, even though it's capable of representing the output that we want. You just have to sort of coax it into getting the weights that actually do it.
So one more thing, I don't know if you are going to get into different levels of convolution, but that becomes important, and I will cover a little bit of that when we go into deeper networks.
Yeah, great. I'm not going to. So,
okay.
Yeah, so with convolutional networks, which are a certain type of these, you see some really cool, like even just visually, you can just tell that in the lower levels of the network, we're sort of representing simple functions, and then as we go through the network, the functions that we are able to represent become more and more complicated. It's pretty cool to like walk through the network and see what the parameter filters look like. Okay, so I've been sort of dancing around this idea of training neural networks. In the very, very simple example, if I just said, find the optimal W1, W2, and B to solve this classification problem, I have a bunch of X1s and X2s, and I have some output Y that I want to predict. You presumably, you've all taken calculus, so you could easily do this, right? You just write down the sum of all the errors, and you take the derivative, and you set it to 0, and you minimize your loss function with respect to these parameters. So that's easy. You just write it down with pen and paper. Couldn't be simpler. Even in very high-dimensional linear regression, it's no longer well, I guess it is sort of a pen and paper thing. You wouldn't write the numbers down, but you can do a sort of matrix calculus version of that, and you can solve for some linear algebra expression that gives you the optimal choice of weights. So this is pretty straightforward. But now, if I gave you this, and I said, okay, these are linear multiplications, and we have some biases, and these are tanh activation functions, and this is a ReLU activation function, this is a Softmax activation function, then you could still write down explicit formulas for P1 as a function of X1. But it's really better not to. It would take you quite a while if you tried to do that, and even worse, if you tried to do the calculus and solve for the optimal weights. Remember that in each of these functions, we have sort of a weight vector that we have to learn. So each of these multiplications can be a scaling by any value. So this is a lot of parameters that we have to solve for. The much, much easier way to do it is to use numerical optimization. So this is a gross oversimplification. But the way that almost all numerical optimization algorithms work, and that's certainly true of training neural networks, is that we make some initial guess for our parameters. So we'll initialize, just like in our, I won't go back to it, just like in our dragon training example, there was some initial value. It was completely arbitrary. It was just whatever, I don't know if it was random or if it was a fixed value, but we had some initial value that was maybe okay or maybe really bad, or I don't know. But from there, we find some direction. We'll keep this very abstract right now. We want to identify some, whether we want to increase or decrease each parameter in order to improve our results, okay? The way that we're going to do this, in particular, is we're going to compute the gradient of our objective function with respect to all our parameters. So by gradient, I, of course, just mean the individual partial derivatives of the loss function. In the regression case, it was just how far away are we from the number we're trying to predict. In this classification case, it's going to be something a bit more complicated. Basically, you can think of it as penalizing predicting a high probability for the wrong class. That's basically what our loss function is. We have some mathematical expression for our loss, so we can write down the derivatives with respect to all the different parameters. We'll go into this in a little more detail later, but at a high level, does that make sense to people that by computing the derivatives, we can see how changing the different parameters will change our loss? And then if we have the list of all the derivatives, we can say, okay, if I update the parameters in this way, then I know that I'm going to decrease the loss, basically. And then we do that, and we repeat, we see how much our objective function changed by, and then we keep doing it until we decide to stop. There are different ways to decide to stop. So this...
Are there, before you click over, are there good ways to get out of local minima?
Yes. In neural networks, I think as soon as you get into a local minimum, you're just screwed. You just stay there forever. So yeah, I wanted to pull up this little visualization here. It's very, very easy to optimize a one-dimensional function, right? In these higher dimensional landscapes, it becomes a bit more complicated. So like Adam just asked, this function here, hopefully people can sort of translate from the contour plot to or the surface plot to the contour plot down here. But our goal is to go from a point like this to the minimum possible value. So in this case, it would be the minimum classification error or the minimum regression error, something like that. In this case, the gradient, I've drawn a little arrow right here. This is the gradient. So in this case, we're in luck because it's going to move us very nicely towards this little trough right here. Adam's point is that when your function is very complicated and non-convex like this, it could so happen, like I deliberately cherry-picked this point so that it would move us in the right direction, but if you are on this side of the surface instead, the gradient is basically just the gradient is technically the one that's pointing up the slope the fastest. So the negative gradient is what we use, but people just call it gradient descent. So in that case, we would actually be going straight into this little trough down here. This is just one of the reasons why training neural networks is very difficult, because there are, quintillions of different troughs in this very, 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 very high dimensional parameter space. And the hope is that the one that you get into is pretty good. That's really the best possible thing that you can hope for. In convex optimization, I don't know if people have studied that at all, you have guarantees that if you follow this sort of procedure, you're going to find the global minimum eventually. In neural networks, there's no global minimum. You're just like, it's chaos. So that's sort of an intimidating thing, but yeah.
Is there a way to add in some kind of like thermal noise in the layers so that if you get stuck in it?
Yeah, so I think that's probably what Adam was alluding to is, in general, in numerical optimization, that's a good idea. Is basically what that means is if we're going down here, if we notice that we've reached like we've noticed that we can't, once we get down here, none of the directions improve our objective function at all. But in this case, we can tell that that's suboptimal, and if we manage to sort of explore a little more, we would get to a better value. What people will do sometimes is they'll basically just perturb their state a little bit and sort of move in a direction at random. And then if they find a new promising direction to look for, they'll keep going down that way, and maybe that'll get them into a better minimum value. I don't really think that people do that in neural networks. I could be wrong, and I shouldn't make broad proclamations, but I think that it really more comes down to taking very, very, very slow steps so that you don't get into a, well, I'm not sure that that's intuitive. It just turns out that if you're careful about initialization and you're careful about not taking too big of gradient steps, usually you end up in a good optimal value. That's another sort of open question is, why is it when we have so many parameters and it's so non-convex, why is it that it usually works anyway? I think that's just sort of, it's even another step beyond the black box, because we don't even know where the black box came from. It just like showed up. The only other, I guess, intuition to take away from this little picture here is what I've drawn. The length of this arrow is actually the derivative in each direction. So this is the negative gradient right here. So if we updated our values to x equals x minus df dx and y equals y minus df dy, then we would get to exactly here. But I mentioned that there's this step size parameter. The intuition behind that is, if this function were very, very flat, we would get to an optimal value faster by taking bigger steps. But if it's very, very steep, then we might hugely overshoot. And so this is sort of a tuning parameter in your optimization, and we'll see this in the exercise too. Actually, I'm going to do another little demo right now where we'll see it some more, but it's usually called learning rate in neural network training because the step size will sort of change throughout the course of the algorithm depending on how well you're doing. So it's sort of the learning rate is sort of the base step size, I guess is the way to think of it. But it's just an important tuning parameter for your optimization. Oh dear, okay. Got a lot more stuff to get through, so I'll try and pick it up in the next couple minutes. Basically, when we're training a neural network, we're doing the exact thing I just said, computing the gradient, taking a step in that direction. But the process of computing the gradient is sort of complicated. So what we're going to do is we have this nice graph representation. So we have our whole computational pipeline decomposed into these little steps. And we know from the chain rule in calculus that the derivative of a composition of functions can be expressed as the product of derivatives of each of the parts. So basically what we do is this clever thing called backpropagation, where first, when we're going to compute our output for our network and figure out our loss function, we go this way. We start at our input and we go all the way to the output. This is just an example of a certain kind of layer that appears. It's called batch normalization. It basically, you see here, we're computing the mean, we're subtracting the mean, we're computing the standard deviation, we're dividing by the standard deviation. That's all that's going on here, is we're sort of scaling and centering our data. So at each of these nodes, we have a very, very simple function that we can write the derivative down for in closed form. So the derivative of this whole bit is going to end up being the product of all of the derivatives in our sort of network. I'm not going to make you guys do any kind of calculus stuff. For the most part, you don't have to worry about doing this because we have these, this is what I was just saying, forward pass is going this way, backward pass is at each step when you're going backward, look at the derivative with respect to the previous step, and then keep multiplying them together. So in general, you don't have to worry about this anymore because we have these frameworks like TensorFlow, Theorem, some that have already been mentioned, and then there's some others that do automatic differentiation. So you don't need to ever, that's not quite true. you generally, if you're using sort of out-of-the-box stuff, you don't need to compute any gradients yourself. You don't have to do the calculus. But it's still, in my opinion, important to understand how this works because of this problem that we mentioned before of getting into these local minima that are actually quite bad and you don't want to be in. So it's important to understand sort of how your training procedure works so that you can diagnose when it's failing. So there's this idea of backpropagation being a leaky abstraction, which means you sort of think you know how it works at a very, very high level, but if your understanding is a bit removed from what's actually going on and you don't understand the gap, then you can sort of get into trouble. We already actually talked about this idea of vanishing gradients, so I'm not going to go into it too much more. There's all sorts of cool stuff on gradient descent out there, so I'll post the slides and you can check out this link if you want to learn a whole lot about gradient descent. All of these algorithms are just different ways of choosing the step size in gradient descent. So basically, as you are moving in a direction and you find that your objective function is getting better and better, some of these will sort of get greedy and start accelerating. They're called momentum-based updates. So if a direction looks promising, you start out taking really little steps, and then as it gets better, you like really start going for it. So it's not really important how these different things work. They're just different ways of deciding what size of step to take. So SGD is basically just the vanilla gradient descent we've talked about. So it's making very, 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 very slow, but steady, always good progress towards the optimal value. Some of these others just like go crazy and lose their minds, but then they sort of figure out that they're doing that and slow it down and then come back. So this is beyond the scope of what we're going to talk about, but there are a lot of different routines like this, and I guess it's good to sort of know that they're out there and then just Google around and see which one people are using these days and use that. That's probably the best strategy. Okay, so the only other thing, I guess we have about 5 more minutes. So if people want to go to this playground.tensorflow.org site, I think this site is really, really cool. It's basically just a little toy neural network that we can configure from scratch ourselves and try out different data sets. So you guys go ahead and go there. I'm going to do the simplest possible problem here, which is I have 2 very obviously linearly separable data sets, and I want to train a linear classifier to distinguish between them. So I'm not even going to use any activation function. I'm just going to take these outputs, take these inputs, multiply by some weights, and get some outputs. So right now, you can see that it's not doing a good job of classifying these. The blue bit is where the orange bit should be, and vice versa. So I'm going to choose a learning rate, and I'm going to say go. And this is going to start doing gradient descent and moving towards a better solution. So because this is so easy, it just found the right solution instantly. It took no time at all. For something like this, it's going to be much harder because there isn't really a good linear separator of these two. So now it started doing gradient descent, and it just didn't get anywhere. So it's still misclassifying about 50-50. So in that case, I'll need to maybe add some more neurons. I don't think that you should necessarily expect to be able to predict like how well things are going to work. It's really, if anything, the message here is just how random and arbitrary it is. That for different data sets, certain architectures will work, and like you can even retrain the same network multiple times, and it'll fail, succeed perfectly, fail. It's sort of it's disheartening in a way. So let's see how this works. So with this one, it just immediately figured it out. And this also has this cool property where each of the individual neurons, if you hover over it, you can see for different places in the input space whether it's activated or not. So this neuron here is sort of learning to distinguish between this half plane and this half plane. And these are other half planes. Basically, these are just a bunch of different half planes, but then when you combine them in different ways, you can learn something pretty complicated like this. This is learning to see stuff that's inside of the circle, or outside of the circle, actually. And then these are different other sort of little projections. This is learning to see stuff that's sort of on the periphery. But now this is basically completely done. If we have something even harder, like this spiral data set, we're going to need some very complicated function to represent these different classes. So I'm not sure that this is going to work. But it's pretty, I don't know, I think it's pretty fun to just watch it try. So you can sort of simultaneously look at the classifications and whether it looks like it's getting the classes right. And you can look at the loss function up here and see how the gradient descent steps are moving us in the right direction. So this seems like it did a pretty good job. There's this piece right here that's being completely misclassified. I expect that if I just restart it and try again, it's going to come up with a completely different shape again. See, now it's having a lot more trouble. It's a very random procedure. Hopefully you guys are playing around with it too.
What does batch size do?
Yeah, so so far I've been talking about gradient descent as compute the gradient for your whole data and then take a step. It turns out that in practice what people do is if you have 100 million images, then you don't want to compute the gradient on all 100 million images and then do one massive update. It turns out that a better approach is to take pieces of your data that we call batches. Now I'll talk about this a bit more in the next session. Take little batches of your data, compute the gradient for that batch, and then do an update just for that one batch. So that's called mini batch gradient descent or batch gradient descent. So in this case, if you use a bigger batch size, you're going to be using more of the data, so you'll get a better choice of gradient descent step, but it'll take longer to do each one. That's basically the trade-off. So are we about, okay.
Is it a good stopping point?
Yeah, this is a good stopping point. If people want to just,
Okay.
I think this is pretty fun to play around with. Maybe you guys can take a little more look at it.
So let's first thank Brett. And I'll ask if there are any questions.
Do you know if neural networks have been used to identify artifacts in images?
Yes.
Yeah. Have there been astronomical applications?
Probably.
What was the question, sorry?
Have there been applications of neural networks to identify artifacts in astronomical images?
Yes.
Oh, cool.
In fact, I'll have some examples.
Nice.
It's becoming increasingly hard to find something that neural networks haven't already been applied for. So you have to like really hurry up and get in there. It's all going to be gone.
Any other questions? Okay, let's thank Brett one more time. And so we're now